Won't know about spring break week. Okay. So we'll let them suffer. Okay. We'll go from current slide. So any questions from anything we've covered so far? Here's Jake. And to my recollection, we are on example 4. Is that right? It's section 5.4. Okay, chapter 5 is analytic trigonometry, and 5.4 is sum and difference formulas. And I think we had gone over what they were, sum and difference formulas. We had done examples 1, 2, and 3, and we're ready to start 4 is my memory. Is that right? Okay. All right, let's go with 4 then. Oh, let me get my pen color back. I can get my pen color back. There we go. Now, here's example 4. Write this. Cosine of, okay, lost my place there. Arctangent, I prefer inverse tangent, but they're doing arctangent, so I'll write it this way, of 1 plus arccosine of x as an expression, as an algebraic expression. Okay? So we want to write that as an algebraic expression. Now, before we get too involved with it, does anyone happen to know what arctan of 1 is? Anybody? What does that mean? The angle theta, say, whose tangent is equal to 1. So tangent theta equal 1. What value for theta could that be? Anybody? Where is the tangent of theta equal 1? That would be where the opposite side is equal to the adjacent side, right? And when is that true? At what angle? 45, of course. Only we're probably going to use radians here, so what would that be? Pi halves is 90. Pi fourths, okay, pi fourths. So why don't we just go and do that first? So let's rewrite this as cosine of pi fourths plus arc cosine. I don't like arcs, but I'll write it. Arc cosine of x. Okay. Now that we've done that, this is just simply, we could have done it up here too, but that was just so much writing. I prefer to write pi fourths. Okay. Now we can do the sum of the cosine formula. Identity, you might say. What is that? Does anyone recall that one? Pretty exciting stuff, isn't it? Anyone remember what the cosine of it? Say again? Okay, so that would be cosine, in this case the u is pi fourths, times the cosine of v, in this case that would be cosine of the arc cosine. I can't write. X, okay. What was the second part? Sine of pi fourths times the sine of the arc cosine of x. Okay. So that's from our sum of the cosine formula. Cosine of a sum of two angle formula. Okay. Cosine pi fourths, I think we know what that is, don't we? Please say yes. Cosine of pi fourths. Okay. Let's go back to our little triangles. Okay. Now, we can choose the lengths of these things anything we want to as long as they're the same. So let's just do 1 and 1. What would be your hypotenuse then? Because tangent is 1, that's the opposite equal to adjacent. 1 and 1, that would be easy. What would be the hypotenuse? Square root of 2. Square root of 2, right? So what would be that's your angle pi fourths. So what's the cosine of that? Square root of 2 over 2. Perfect. So this will be square root of 2 over 2. Now, what's the cosine of an arc cosine? X, whatever the argument is. So that is just going to be an X there. Minus, how about sine of pi fourths? You want to hazard a guess there? It's also root 2 over 2. Okay. Uh-oh. Got a problem, Houston. You can't do a sine of an arc cosine. Unless you draw a little triangle. And we like little triangles, don't we? Okay, so let's draw a little triangle. Okay. Okay. First, we need to know what this angle theta is. And let's just name it theta, for lack of anything else to name it. And if that is your angle theta, and that's what this is, angle theta, how's another way to write that equality I just did when I put the equal theta there? Cosine theta equal x. Okay? Now, I usually like to see my cosines and sines and tangents as ratios. So what can we write as that ratio? X over, still have the same value. 1. Okay, let's just write that as x over 1. Now, what does that tell you? What is cosine the ratio of? Really? I thought that was psi. Caught some old hen. No, we won't. Caught another hen, right? So that's cosine is adjacent over hypotenuse. So that makes hypotenuse 1 and the adjacent side x. Okay? Now we can say what's the sine of that same angle theta, right? Because that's what theta is. What is the sine of that angle? This one's the opposite. Opposite. Oh, but we don't know the opposite, do we? And there's no way in the world to get it, is there? Pythagorean theorem, okay? What would that give it to us as? One minus x squared, yeah. The square root of 1 minus x squared. Perfect. Okay? So, now we can write minus this, and the sine of that angle is the square root of 1 minus x squared. Okay? And let's see, let's just factor out your root 2 over 2. Get out of there. Okay? Factor out the root 2 over 2, and that leaves you x minus the square root of 1 minus x squared. There is that expression written as an algebraic expression of x. They don't say of x, but that's what it is. Okay. Does that make sense? No trig involved. It's all algebra. Make sense? Okay. Let's see how the book did it. Oh my goodness, what in the world did they do? Well, goodness gracious. Whew. Okay. What they did, they multiplied everything by root 2, I think. I sure hope that's what they did. That would be x times root 2. I know they write it root 2x, but I prefer to do it that way. Minus, then they multiply root 2 by that, so that would be the square root of 2 minus 2x squared all over 2. Yes, that's how they wrote their answer. I'm so delighted they chose to do that, and I'm delighted that Caitlin is here as well. All right. I see no reason to complicate it and do that, but that's how they wrote their answer. Same answer. If you have that answer, it's perfectly fine. Okay. They chose to write that. Now, the reason I don't like to write square root of 2x, I know that's standard form, because sometimes with my writing, that line may get a little long, and then I might not know if the x is inside or outside the house, and I might make an assumption that's wrong. This way, I know the x is outside the house, so I tend to do it that way. The book always does it the other way, and you have to look carefully to make sure the square root sign ends over the 2 and doesn't extend over the x. But that's their problem, not mine. Okay. All right, any questions on that? There is a checkpoint after every example they give. Please take advantage of those. Okay. So I think they have example 5 on the slide set. So let's scroll through example 1. Yes, they do. All right. And by the way, example 5 is also at larsonprecalculus.com for an interactive version of this type of an example. It says verify. This says prove. Let's make sure it's the same problem. Yes, it is. Okay. It says use the difference formula to prove the cofunction identity. We've already been dealing with this. In the text, it says verify the cofunction identity. Same one. How would you do this? Using the difference angle formula. That would be cosine of pi halves times the cosine of x. That's the first part. Plus. Excuse me just a second. Let me get Jemiah here. Okay. Plus, continue, sine of pi halves times the sine of x. Now the question is that equal to sine x? We've been saying it is, but is it? Well, let's see. What is cosine of pi halves? Anybody? 0. So this term goes to 0. What's the sine of pi halves? 1. So that sure enough says that sine x is equal to sine x. Yes, verified. So we were right all along that the cosine of the complement of an angle is the same as the sine of that angle. Good deal. And that wasn't very hard to demonstrate at all, was it? Anyone need a little longer? Okay. Let's see how they do it. Using the formula for cosine u minus v, you have cosine u, which is cosine pi halves, times cosine v, which is cosine x, plus, remember with cosine, the sign flips, okay? Sine of pi halves times sine of x, okay? But we know that the cosine of pi halves is 0. So cosine of all the half pi's are 0. Starts at 1, goes 0 at pi halves. So the first term becomes 0. Sine of pi halves is 1. And that's just 0 cosine x plus 1 sine x. That's equal to sine x. And that's the right-hand side. All right. Now, that was example 5. Trying to find the verbiage. Okay, right under 5 it says, sum and difference formula can be used to derive a reduction formula for rewriting the expression such as sine of theta plus pi n pi over 2 is cosine of theta plus n pi over 2. You know, when we have a general formula and we have those plus things, so we can rewrite those as trigonometric functions of only theta, leaving out the other things. So that's where example 6 comes. Those are called reduction formulas. Okay? They're skipping example 6. So let's do example 6 and then we'll erase and come back to 7. Write each expression as a trigonometric function of only theta. So here's the first one. Cosine of theta minus 3/2 pi. Okay? Where would you begin? Anybody? Earth to class, come in please. Okay. Where would you begin? Cosine theta, is that what I heard? Okay. Next. Cosine of 3/2 pi, 3 pi over 2. Next. Anybody? Not minus. Remember, cosine, you flip signs. Plus. Next. Anybody? Sine of theta. I feel like a dentist up here pulling teeth. Okay. Next. Sine of 3/2 pi. All right. We finally got that part done. That was the easy part, right? Okay. All right. And remind me again, what is cosine of 3/2 pi? 0. Cosine of all your half pi's are 0, so that's certainly, so this goes to 0. And so we got a sine theta, and what's sine of 3/2 pi? -1. So this thing here is equal to negative sine. Okay. Yep, that's what they got to. All right. Let's see if there's room to do the B part here. The tangent. Oh, we haven't used this one, have we? I don't believe yet. Of theta plus 3 pi. All right. Ooh, this one we all have to turn back, don't we? And see what the tangent of, it's a sum, right? Yep. What's that? Tangent theta plus tangent 3 pi over 1 minus tangent theta times tangent 3 pi. Okay. Now, tangent theta will stay tangent theta. Plus, What in the world is a tangent of 3 pi? Anybody? 0. And why is it 0? Because tangent of 0 is 0, remember? It goes up and down from 0, right? And what's the period of tangent? Pi. So at pi, it's going to be 0. At 2 pi, it'll be 0. At 3 pi, it'll be 0. 4 pi, negative 2. All those pi's is going to be 0. So that's going to be a 0 there. So we have a tan theta in the numerator. That's all that's left there. So I'll erase, well, I won't erase, will I? I'll try to erase my plus sign, okay? And what goes in the denominator? 1. So what is your answer? Tangent theta. Which, of course, what we were just saying, tangent of theta plus a multiple of its period is going to be tangent of theta, okay? Well, wherever you go, if theta is right here, so there's your tangent theta, and you go 1 pi over, it's the same value. 2 pi over, it's the same value. 3 pi over, it's the same value. It's going to be the same as tangent theta. Very good. All right. There is a checkpoint at the bottom. Might be a good idea to do that as well. Soon after class as you can. Okay, now we're ready for example 7. Find all the solutions of sine x plus pi fourths. On the slide, they have something wrong here, don't they? They have 2 open brackets and no closed brackets. There's a closed bracket there and a closed bracket there. Okay, shame on them. Okay, and that's equal to -1 on the interval 0 to 2 pi. Okay. Stomach says it's lunchtime, and we're a long time from lunchtime. Okay, so how would you begin? Where would you begin? Okay. Yeah, the sine of the sum of 2 angles. And that would be sine of x. Help me? Not sine. Cosine of pi fourths. Next, plus cosine x sine of pi fourths. Okay, that's the first part. Okay, plus, now the second part. Sine x cosine pi fourths minus cosine x sine of pi fourths. Who didn't plan ahead very well here? And that's equal to -1. We want all the solutions on the interval 0 to 2 pi that make that true. Well, let's fill in what we know. Okay, what is cosine of pi fourths? Root 2 over 2 times sine x. Okay. And before we get too far carried away here, let's take a look. Step back. Okay, here's a cosine x sine pi fourths, and there's a minus cosine x sine pi fourths, right? They add to 0, so I don't have to evaluate there. I'm lazy. Okay. So then we got what? Plus, and what we got there? cosine pi fourths is again root 2 over 2 times sine x. And we have this equal negative 1. Okay, that fit on there a lot better there, didn't it? Okay. Same terms, so we add them together, and what does that give us? 2 of those will cancel out the denominator, so it's just root 2 times the sine of x is equal to minus 1. Now what? Yep, and how do we do that? Divide both sides by root 2. Okay, so that gives us sine x is equal to negative 1 over root 2. Now, if you don't like the way that looks, you could write it how? Negative root 2 over 2. And then you ask yourself, what angle x, when I take the sine of it, do I get negative root 2 over 2? But you need to be between 0 and 2 pi. Well, I know it's no angle in the first quadrant. Why?
It's negative.
Yeah, it's negative, so it can't be in the first quadrant. How about the second quadrant? Sine is positive in the second quadrant. Can't be there either. How about the third quadrant? Could be. Where, at what angle? Now, the third quadrant gives you a negative sign, so we got that established. So, what angle gives you, the sine of what angle gives you root 2 over 2? Pi fourths, exactly. So this could be, and what would the, if that's the reference angle in the third quadrant, what is the actual angle? To get over here, you have to go pi plus 1/4 pi would be 5/4 pi. So that's 1. X equal 5 pi over 4. Okay? But you can keep going, and sine is still negative in the fourth quadrant. And you still have a reference angle of pi fourths. So what's 1/4 pi short of 2 pi? 7 pi over 4. So there are 2 possibilities. Those are the only 2 in between 0 and 2 pi. Couldn't be the first half of that trip because the sine is positive in both the first and second quadrants. But there's 2 places where it's negative in the below the line. That would be in the third and the fourth quadrant. And since your reference angle in both places is pi fourths, that would be 5/4 pi and 7/4 pi. Okay, that's how we did it. Let's see if they did it any differently. All right, to erase. Okay. Using the sum and difference formula, we rewrite the equation up above to be that, which is just like we rewrote it. And they notice here, they didn't evaluate that. They notice that these 2 go out and that you have 2 sine x times the cosine of pi fourths equal negative 1. Okay? Adding those 2 together. Then they evaluate that to be root 2 over 2, and that 2 divides out that 2, and you have root 2 sine x is equal to negative 1, divide both sides by root 2. Sine x is equal to negative 1 over root 2, or written as negative root 2 over 2. Then they ask themselves what angle. The only solutions on that interval would be at 5/4 pi and 7/4 pi. So yep, they got to the same thing we did. Just about the same way too. Whoa! And they're skipping example 8. Shame on them. All right, so let's any questions on the 7? I can bring it back if you need it. Any questions on 7? Okay. Let's do number 8. Applications on calculus. All right. Verify this, that the sine of x plus h minus sine x divided by h. Verify what in the world that is. Well, yeah, we'll do it. Since it says verify, we'll write down the other side, knowing, of course, you can't cross the equal sign in your verification. They say this is equal to cosine x times the sine of h over h no. I said it right, but wrote it wrong. Okay. Okay, that's better. Minus sine x times 1 minus cosine h over h. All right. That's why last night before I went to bed, I said, I've got to verify that. Okay, right. One of my favorite. Never mind. Okay, so how can we verify that? Even though the right-hand side looks pretty nasty, let's deal with the left-hand side. Usually you start with the most complicated side and work the other way. This one, no, we have a trig identity we can use for this right here. What is that? Or maybe we do. Sine of x cosine h plus cosine x. Get out of there. Okay. Sine of h, right? That's the first part of the numerator, minus sine x, all divided by h. Right? Okay. Now, notice what they're going to be doing here to get this to look like that. They're separating the cosine x's from the sine x's. So let's rearrange this and get our sine x's together and our cosine x's together. So that will be sine x times cosine h over h, right? Minus sine x. Okay, those two are together now. And then what you have left is plus a cosine x times sine h over h. Okay. Whoops. Okay, I forgot my over h there. Okay. Right? Okay. Now, we got the sine x's here, cosine x's there. So let's factor out the sine x, okay? And what do we have left? Sine x times, here's a cosine h minus 1 all over h, plus a cosine x, and what do you have left there? Sine h over h. And that's, oops, okay, not quite what we have before. Okay, what they did was reverse these two, so, and reverse the overall order. So let's write the cosine x over sine h over h minus, now what we're going to do is reverse the sign of these two, reverse the order of those two, which is going to negate this. So that's why it becomes a minus sine x times 1 minus cosine h over h. Sorry, I ran out of screen there. Now we've got them looking exactly the same. Okay. And you might say, Why would we do that in calculus? Well, when you get there, you'll see. But this form right here is basically your difference quotient. You remember that from pre-calculus algebra? Sine of some function of x plus h minus sine of x divided by h. X plus h minus x is just h. Okay, so that's your difference quotient, which is what we use for a derivative. We take a limit as h approaches 0. So as h approaches 0, if we go to this form, sine h over h, then you see this and do it in calculus, that's equal to 1. So the derivative of sine is cosine. But, well, so far. Here, the limit is 1 minus cosine h over h, and you'll also see that that's equal to 0. So this term disappears, this becomes 1, so the derivative of sine, which is the function you have, is cosine. And you will find that to be true in calculus. Always. Okay. That's where you use that. And then they also do the thing for cosine, and you can do that as well. That's your checkpoint. Vocabulary. Some of our favorites. Sine of u minus v is?
Sine u cosine v plus, or minus.
Minus.
Cosine u sine v.
It's the same thing you just said. Cosine u sine v. Okay, right. All right. Sine. Okay. Number 2, what's cosine of u plus v? It's what?
Cosine u, cosine, 4 times cosine v.
Right.
Minus sine times
Sine v. Perfect. Number 3, tangent u plus v. Flip, flip, flip. Okay. Tangent u plus tangent v,
divided by
1 minus
tangent
times tangent v. Perfect. Number 4, sine of u plus v.
sine u cosine v plus cosine u sine v.
Perfect. Number 5, cosine of u minus v.
Cosine u and cosine v plus
Yes.
sine
Sine u sine v. Perfect. And tangent of u minus v.
tangent u minus tangent u
Good.
divided by 1 plus tangent u times
Perfect. Perfect. Homework exercises here. Do either 7 or 9 or both. They have 2 parts. They're both at Calc Chat. The answers are at the back of the book. The Calc Chat gives tutorial help and worked out solutions. Do any of the odds 11 through 25. They're all at Calc Chat. 21 happens to be at Calc View. Do any of the odds 27 to 33. They're all at Calc Chat. Do any of the odds 35 to 39. They're all at Calc Chat. 35 is at Calc View. Do any of the odds 41 to 45. They're all at Calc Chat. 43 is at Calc View. Do any of the odds 47 to 51. They're all at Calc Chat. Do 53 or 55 or both, and they're both at Calc Chat. 53 is at Calc View. Do any of the odds 57 to 63. They're all at Calc Chat. 59 is at Calc View. Do either 65 or 67. They're both at Calc Chat. 67 is at Calc View. Do any of the odds 69 to 73. They're all at Calc Chat. 73 is at Calc View. Do either 75 or 77 or both, and they're both at Calc Chat. 79 is a simple harmonic motion or harmonic motion problem, so that's should be at Calc Chat. There's a couple true false, 81 and 83. They should be at Calc Chat. There's an error analysis, which I really don't care for that much because they print something wrong in the book, but they tell you it's wrong. You figure out what's wrong. And then verifying some identities, 87 and or 89. They're both at Calc Chat. 91, 93, they're both at Calc Chat. 95 is at Calc Chat. 99 is at Calc Chat. And 101's a proof It should be at Calc Chat. If it is, you can try to follow that too. Any questions? Okay. That then, oh, no, that was example 8 we just did. So we've already done example 7. So let's go to .8. I don't know what's the problem here. Oh, that's the problem. My thing had scooted over, so I couldn't get to the box. Okay. So 5.5, the last section in Chapter 5, which means before you leave today, pick up the Chapter 5 test. Now, we won't get finished everything, but at least it'll give you something to do over spring break, so you won't be there cursing me for not giving you plenty to do over spring break. So, be sure you get that before you go. Now, I'll go over what you should be able to do and what you can hold off and wait on later. Okay, Chapter 5 is analytic trigonometry. The last section here is multiple angle and product to sum. They'll also do sum to product formula. They give you some more identities because they didn't think you had enough to keep you busy. So multiple angles will give you some more identities. Half angles will give you more identities. Product to sum, you'll use sometime, but not that frequently. Sum to product, even less likely, but you will use it occasionally. You can always look them up if you need them. But you get plenty of more tools to put in your belt and use them if and when you ever need them. My first classroom was way too hot. This one's a bit cooler, but I can't get my buttons to work, so I'll worry with those later. All right, so 5.5. Objectives here use the multiple angle formulas, which we haven't had yet, but we will, to rewrite and evaluate trigonometric functions. We'll use power-reducing formulas, which we haven't done yet, but we will, to rewrite and evaluate trigonometric functions. We'll come up with some half-angle formulas, and we'll use those to rewrite and evaluate trigonometric functions. Got an idea we're going to be rewriting and evaluating trig functions. We'll use product to sum and sum to product formulas to rewrite and evaluate trigonometric functions, and we'll use some of those formulas to rewrite real-life models, okay? Which basically hopefully means actually solving some equations, not just rewriting formulas, okay? And I can't get this to work, but anyway. So, let's start with our multiple angle formulas, and guess what? You already know them. Almost, but close enough, okay? In this section, we'll study 4 other categories of trigonometric identity. First category involves functions of multiple angles, such as sine of KU and cosine of KU, where you have multiple angles, not sum or difference of angles. Before we were adding and subtracting angles, now we're multiplying angles. The second category involves squares of trigonometric functions, such as sine squared of u. And guess what? You already have all the tools you need for that as well. Okay? Guess what? When you see those squares, think Pythagorean identities. Okay? The third category involves functions of half-angle formulas. Well, if you can get double angle formulas up here, we should be able to sort of kind of like undo that and get half-angle formulas. Well, we actually need something from here too, so we'll get that. And the fourth category involves either products of trigonometric functions such as sines and cosines multiplied by cosines, and then we'll do sines and added to cosines. And guess what? You really have all the tools you need to derive those as well. Okay, so you should learn the double angle formulas because they're used often in trigonometry and calculus. So before we just launch into learning them, let's figure out what they are. I want you to remind me of something. This is from a long time ago, so hopefully you can remember. What's the sign of u plus v? Dig deep into the memory banks here. Sign of u plus v. I'm kidding, huh? Sine u, cosine what? V, plus cosine u, sine v. Ah, good. You have good recall. Okay. Oh, you looked. Okay. Now, here's the question. What happens if u is equal to v? What does the left-hand side give you? Sine of 2u, right? Happy sine 2u. Okay, never mind. That's equal to, if u is equal to v, what does that? This is sine u, cosine u. If u is equal to v, v is equal to u, right? Plus cosine u, sine u. If u is equal to v, right? Well, what's that? 2 sine u cosine u. 2 sine u cosine. There's sine of 2u. That's not worth memorizing. You can just get it. If you knew the other, which of course Christian did without looking, you got this one. Just like that. Don't bother memorizing. You just get it. I mean, it's right there. Would you think we can do anything like that with cosine? What was cosine of u plus v? Anybody? I know it was a long time ago, but we can remember, can't we? Cosine u, cosine v, minus sine u, sine v. Oh my. And then guess what we're going to do? Let's say, what happens if u is equal to v? What does the left-hand side become? If u and v are the same, this is cosine 2u. Happy cosine 2u. Okay. Next. What's the right-hand side becomes? Say again? Cosine squared u. Because cosine u and cosine v are the same. If u and v are the same, that's cosine squared u minus sine squared u. Look at that. Those are pretty easy, aren't they? Really easy to get. Okay? And that looks different, but fairly similar to your Pythagorean identity. Your main point. We're going to come back and use that in a little bit. Okay? Let's see if we can do tangent the same way. I don't think it works quite as easily. Well, they don't even, yeah, they do. Okay. Well, before we do move on to tangent, like I said, this looks a lot like a Pythagorean identity, doesn't it? Give me two ways to express the Pythagorean identity other than sine squared plus cosine is equal to 1. What is sine squared by itself? Come back. Wait, yeah. If you subtract cosine squared from both sides, what you get? Pythagorean identity. Let's start with this one. Sine squared u plus cosine squared u is equal to what? 1. Okay. Now subtract cosine squared u from both sides, and what do we get? 1 minus cosine squared u. Okay, so let's plug that in here. Minus a 1 minus cosine squared u. Okay? So this is cosine squared u minus 1. Minus a minus is plus cosine squared u. And guess what that gives us? Combine like terms. 2 cosine squared u minus 1. Okay? All right. Hang on to that thought too. We're going to come back and use it. Let's do the same thing here. Cosine squared u is equal to what? From your Pythagorean identity. 1 minus sine squared u. Okay? So this time, we'll, instead of cosine squared u, we'll write 1 minus sine squared u. Then we'll do a minus sine squared u. And guess what we get? One minus 2 of them, aren't there? 2 sine squared u. So we actually have 3 different identities for your double angle for cosine. Cosine squared u minus sine squared u. But if you don't want 2 different functions there, you can get a equation for the cosine, and that would be 2 cosine squared u minus 1, or 1 minus 2 sine squared u. So we have 3 different identities for the double angle formula. Only one for the poor little sine angle, double angle formula, but we got it. We haven't done the tangent yet. Let's see if we can do that. Similar to what we did before. What was, are we running out of time? Oh, I thought someone said something. How are we doing on time? Oh, good. Yeah, plenty of time. Okay. What is tangent of u plus v? Oh boy, a long time ago. What's that? Tangent u plus tangent v over 1 minus tangent u tangent v. Right? What if u is equal to v? What do we have on the left? Tangent of u is equal to v, that'd be u plus u, right? That'd be 2u. Happy tangent to u. Okay? And if u is equal to v, what you got on the right-hand side? 2 tangent u over 1 minus tangent u squared. Okay. No, tangent squared u. Duh. If I had put parentheses in there, that would have been all right, but I didn't. Okay, tangent squared u. All right, and that's what you get. They got to. So we had these just based on the others, right? And they're pretty easy to see. So here they are, written out for you, but we already knew them. Sine of 2u is twice the product of sine and cosine. Cosine u. Sine u cosine. Cosine 2u, on the other hand, is 3 different representations. The difference of the squares with cosine squared u minus sine squared u. 2 cosine squared u minus 1, or 1 minus 2 sine squared u. All 3 representations. 1 with 2 functions, 2 with 1 function each. And then tangent of 2u is 2 tangent u minus over 1 minus tangent squared u. Pretty straightforward and easy to get. Even if you don't want to memorize them, they're easy to get if you know your others. Big if, okay? Or write them down or look them up. You know, that works too. Anyone need those longer? Okay, sorry. Just derived them all, but there you've written them there. And let me meet your computer. Does anyone else come in since I called roll? I wasn't paying attention. Missing. Okay. All right. I just happened to this dawn on me. Just wanted a quick reminder. This is a commercial message from your local teacher. I think I've mentioned this before. Just about every class, maybe. Papers, 1, 2, 3, 4, 5 have turned in papers. I may have got one more today. I think so, yeah. So that leaves something like, is it 16 of you that haven't turned in paper? No, 16 total. So 10 that haven't turned in the paper yet. Well, you've got time, but guess what? Let's see. Oh, next week's spring break week. You have a whole week to work on your paper. How wonderful. All right. I'm glad I remembered this, okay? Test 1. I have 2 people who have not turned in test 1, okay? Test 2, a lot more. Fewer than half of you have turned in test 2. And then I'm giving you test 3 today. You won't be able to finish it, or you could, but you don't have to because we're not going to quite finish 5-5. But I did want you to have something to do over spring break. Otherwise, you'd be very angry with me, I know. So wanted to accommodate you there. So let's do example 1. Solving a multi-angle equation. See, I knew we were going to be solving equations, not just writing expressions, solving equations. Now, anything wrong with this picture? That equation? Well, one thing that first glance, 2 different trig functions, okay? Going to be hard to factor anything out there, isn't there? But not only that, the 2 different arguments for trig functions, so you can't even relate the 2 very well. So what might we choose to do? What new identity we just pick up? Anybody? Double angle formula. Yeah, we can do that. Well, the 2 cosine x stays 2 cosine x. Okay? But what does sine 2x become? 2 times the sine of x times the cosine of x, and that's equal to 0. Now, even though that's a little bit longer, it sure has a lot more promise, doesn't it? Because what can you do? Factor out what? 2 cosine x? Is that what you said? 2 cosine x. And what have you got left? 1 plus, second, sine x, and that's equal to 0. Now, they didn't put any limits on this one, so we're going to have to do all our possibilities here. So, where do we begin? Set each of them equals 0. So either 2 cosine x is equal to 0, or 1 plus sine x is equal to 0. 2 cosine x equals 0. What can we do with the 2? We can divide both sides by 2, and we're through with the 2. That's legal with equations, okay? So that leaves you cosine x equal 0. Now, where is that true? All of your half pi's. So that'll be pi halves x equal pi halves plus n pi, because you have not just 1 every cycle, but 2 every cycle at 1/2 pi and 3/2 pi. 1/2 pi is going downhill, 3/2 pi is going uphill, so you have 2 every cycle. So that's n pi.
Plus 2 n pi?
Okay. It is 2 n pi, but then you'd have to do another one for 3/2 pi at 2 n pi. But guess what? They're exactly n pi apart, so let's just make them n pi. Because they do come, see, the zeros are at regular at every pi. The period is every 2 pi, but the zeros are every pi. Any other value wouldn't be, but, 0 would be. All right? Now, how about this one? What do we do with that one? Second? subtract 1 from both sides is another way of saying that. And that would give you sine x is equal to -1. Where does that happen? Is what? At pi halves? At pi halves it's +1. Where is it -1? 3 halves pi. Okay, x equals 3 halves pi. Now that one occurs every 2 pi plus 2n pi. But guess what? 3 halves pi is also counted in this one, right? So this covers both of them. Okay, that should cover both of them. Now, when they wrote them out, they did the 2n pi for both of them, but you could just, because those are, it's these two and those two and those two and those two, but that's every n pi. Okay, so you could shorten it just that. Or you could write it that way. Nothing wrong with it. Ooh, I'll turn my book there. Shame on me. Okay. All right, we still got some time. Oh, let's see how they did it. Now, I bet you'll see they do it the other way. All right to erase? Okay. Begin by rewriting the equation so that it involves functions of x rather than 2x, then factor and solve. So first they write down the equation again, which is an incredible good use of time. And then they rewrite sine 2x is 2 sine x cosine x, which again makes it a little longer, but now you can factor. So they factor out a 2 cosine x from both sides, leaving you 1 plus sine x, and that's all equal to 0. So either 2 cosine x equals 0, 1 plus sine x equals 0. And this will give you the first, they just went right to the chase here. They said it's at pi halves and 3 halves pi, and that one's at 3 halves pi. Those are all the solutions between 0 and 2 pi. To give your general solution, we do so much easier just to do. See, the difference between those two is pi, right? 1 half pi minus 3 halves pi minus 1 half pi is pi, right? 2 halves pi, which is pi. So that's just every pi then. But they put them this way, general solutions. Pi halves plus 2n pi, and 3 halves pi plus 2n pi, which you could have just written as pi halves plus n pi, for n is any integer. And it says, try verifying graphically. Yeah, if you got a graphing calculator, knock yourself out. Okay. That was example 1, right?
They skipped 2 and 3.
What's that?
They skipped 2 and 3.
They skipped 2 and 3. So let's us go back and do 2 and 3. Or at least 2. We may not have time for 3 today. We might. Let's see. Example 2. Use the conditions below to find sine of 2 theta. So we're looking for sine of 2 theta. We're also looking for cosine of 2 theta. And we're also looking for a tangent of 2 theta. And here are the conditions given. That cosine theta is equal to 5/13. And that 3 pi over 2 is less than theta, and that's less than 2 pi. Those are the conditions. Okay. Now, what do those conditions tell you? Cosine theta equals 5/13 gives you an angle, but I mean, gives you something about it. But where does it put you? Either in the first quadrant or the fourth quadrant, because cosine is positive first and fourth. That tells you you're in the, you're between 3 halves pi and 2 pi, fourth quadrant. Okay, so that alone would have told you that. Okay, but you needed to know the value as well. Okay, now my suggestion if you haven't gotten used to this yet, get used to it, is draw you a circle. Okay, I'm not going to say a unit circle because it's not. Anyone want to guess what size circle that is? Not a unit. It's a 13 circle. Why? That's your denominator. That's your R. Okay? So 13. Let's just say this would be 6 and 7. Half of 6 is 3, so that will be 1 and 2. That will be 4 and 5. Halfway between 7 and 13 would be 6, so that would be, half of that is 3, so that would be 10. And that would be 8, 9, and blah, blah, blah. Okay. You got the general idea? Okay, do the same thing down here since you're in the fourth quadrant. Let's do 6 and 7 because they're near the middle of it. That'll be a 3, that'll be a 1, 2, and a 4, 5. That will be a 10, that'll be 8, 9, and that will be 11 and 12. Okay. That's not really helpful, but just to give you an idea. Okay. Now, the cosine theta is 5/13. And cosine is what? Adjacent over hypotenuse. So adjacent here would be 5. 1, 2, 3, 4, 5. And the hypotenuse would be down here. So this is approximately this angle right there. That would be the theta we're interested in. I use the reference angle theta to get us there, but that would be about the angle. Now, if that is indeed the angle we're talking about, what would be, okay, we'll just leave it there. Cosine theta is that. So, my question then is, how do you get sine 2 theta? Sort of looks like you doubled the angle, doesn't it? So what formula might we use? The double angle formula. What a clever idea. Yes, and what? That's what would that be? 2 times sine theta times cosine theta. We already know what cosine theta is, don't we? 5/13. But do we know sine theta? Now remember, it's the same theta, and it can even be considered the same as this theta. Okay? Whichever. Okay? What would be the sine of that? Or how could you get it? Second?
Negative 12 over 13.
Yes. Did you happen to know that, or did you do Pythagorean theorem? Certainly will give it to you. You know it's got to be the sine, the opposite side is negative. Y is negative. So you're absolutely right. This is negative 12 over 13. Pythagorean theorem will tell you that. So what do we have? Yuck. 12 times 5 is 60, times 2 is minus 120 over 13 squared, I think, is 169. Is that right? 169. Okay. So there's your sine of 2 theta, right there. How about cosine 2 theta? What would that be? Anyone remember that one? It's what? I would pick one. And which one would you pick?
Cosine squared theta minus sine squared theta.
That will certainly work. He likes to work hard, I can tell. If you chose the one with only cosine, we already know what cosine is. So if Patrick happened to have made a mistake when he was doing his sine, we would still be okay, right? So why don't we use that one? Does anyone remember how that one goes? The one that only has cosine in it. That's 2 cosine squared theta. Is that what you said? Minus 1. Okay, so let's plug that in. 2 times, and your cosine theta is 5 over 13, so that would be 25 over 169 minus 1. Well, boy, that's a very small number, isn't it? That would be 50 over 169 minus 169 over 169. That's about a 119, isn't it? A negative 119 over 169. All right. Now, tangent 2 theta. How do we get that one?
2 tangent theta over 1 minus tangent.
He really likes to work hard, doesn't he? Okay? You certainly can. It works. But guess what? Else that's tangent 2 theta is sine 2 theta over cosine 2 theta. And for lazy people like me, that would be minus 1 over 120 over 169 divided by minus 119 over 169, which would be minus divided by minus is plus. The 169s you can divide out, 120 over 119. Awfully close to 1. Not quite, but close. Does this even make sense? Okay? If theta is here, 2 theta would start here and go, see, that went 1, 2, 3 complete quadrants. Plus a little bit. So from here we'll go 1, 2, 3 complete quadrants plus a little bit. That puts us down here somewhere. Okay? What quadrant do you wind up in? Third. And what's the sign in the third quadrant? Negative. What's the cosine in the third quadrant? Negative. What's the tangent in the third quadrant? Positive. Look at that. That puts you right about there. Close to 45, not quite, awfully close to 45. That looks reasonable, doesn't it? So I would say we probably did that okay. There is a checkpoint. Please do the checkpoints. They don't have this little paragraph here. No, they don't. Okay. We'll begin next time with, example 3. Next time's a long time away, about a week and a half. Get over it, okay? Homework exercises here in this section. We didn't get as far along as probably you wanted to, but we did move. So do any of the odds 7 through 13. They should all be at Calc Chat, 9's at Calc View. Think you can do 15 through 19, any of those odds. Those should all be at Calc Chat. Think you can do any of the odds 21 to 21 or 23. They should both be at Calc Chat. 21's at Calc View, and we'll hang off on from 25 on. Okay, so that gives you some homework to do, but y'all would finish that in probably tonight, wouldn't you? So you need a lot more than that, right? Okay, absolutely. Okay, so let's see if I can find test 3. Oh, I bet you I forgot to have it. Oh, no, here it is. Okay, we got, oh, I'm sort of kidding, but no, it isn't there. Okay. There we go. I was in the alpha part, not the trig part. It's back here. I know it is. I'm getting closer. Warm. Ah, here we go. All right. Good deal. Happy spring break. This is my gift to you. Okay? Now, don't sweat doing all of it, but you can at least get started on it. Okay? If you hang on just a minute, I'll tell you how far you can go next to what we've done so far. You see Bree?
Oh, yeah,
I know you could be disappointed if you didn't get one for us. Okay. What's that? Oh, okay. Now, I think you can do 2. Well, they're sort of mixed up in here. I think that 14 through no, you can do 14. You can do those. I think the one maybe you can't do is 18. Maybe just 18. You might even be able to do that. Okay. So I think you can do just about all of it. Maybe not 18. And maybe some of the others too. Hang on. If you can't do them, hang on, ask about them. We'll see. But at least it gives you something to play with. Since y'all gave me some things to grade, now what did I just do with the things she gave me? That almost got lost forever. Okay.
Happy good spring break.
You too. Thank you. Thank you. You know, I need something coming back.
Yes, sir.
Okay, because this is the third test. I still haven't gotten either of the first two.
Yes, sir.
All right.